In 2050, humanity faces its most critical deadline: net zero emissions. The problem? Classical computers, the machines that have powered everything from Netflix to nuclear weapon simulations, are hitting a wall. They simply cannot solve the molecular puzzles required to stop climate change in time. Meanwhile, a radically different kind of computer is emerging: quantum machines that exploit the bizarre rules of quantum mechanics. These devices could accelerate climate solutions by 10,000 times or more. But here's the tension. One of these paradigms will dominate the 2050 climate race. Or will they? In this video, we're going deep into the physics, the money, and the timeline of humanity's computational battle for survival. For 50 years, we've followed Moore's law. The number of transistors on a chip doubles every 18 months. This exponential curve gave us smartphones with billions of transistors, supercomputers with trillion calculations per second, and the ability to simulate entire weather systems on silicon. But there's a fundamental problem approaching fast. We're running out of room. Modern transistors are already just nanometers wide, approaching the size of atoms themselves. At this scale, quantum effects start destroying the logic gates. Electrons tunnel through barriers they shouldn't. Heat balloons. You can't miniaturize further without violating the laws of physics. What does this mean for climate change? Today's best climate models, the ones that guide trillion-dollar policy decisions, run at about 20 to 50 kilometers of horizontal resolution. That's the size of a single grid cell in a global climate simulation. Think about that. A Colorado thunderstorm is 10 kilometers wide, but your climate model can't resolve it. It just approximates thunderstorms using statistical formulas. These formulas introduce systematic biases that compound over decades of simulation. Underneath climate models are partial differential equations, Navier-Stokes equations for fluid flow, energy conservation laws, radiation physics. Classical computers solve these by discretizing them into a 3D grid covering the entire planet. But higher resolution means exponentially more computation. To go from 50 kilometers to 5 kilometers resolution, a 10x improvement, you need 1,000 times more calculation. Today's most powerful climate supercomputers, like the 1.2 billion pound Met Office machine in the UK, consume 13 megawatts of electricity. That's the power of a small town. And they still can't achieve the resolution needed. The bottleneck is physics, not engineering. Here's the hard truth. Classical computers can't solve the climate crisis alone. Not because engineers aren't clever. Not because we lack funding. But because the problems are fundamentally too big. Take nitrogen fertilizer production, the Haber-Bosch process. It consumes 3% of the world's energy. That's equivalent to the entire aviation industry. Why? Because the catalysts used are crude approximations, not optimally designed at the quantum level. The optimal catalyst is locked inside an enzyme called FeMoco, which bacteria use to fix nitrogen from the atmosphere. Scientists have spent decades trying to understand it. If you tried to simulate FeMoco using classical computers to calculate the quantum behavior of electrons in the active site, you would need 800,000 years of supercomputer time. That's not an exaggeration. That's the actual scientific estimate. Now imagine a completely different kind of computer, one that doesn't use bits, zeros and ones. Instead, it uses qubits, quantum bits. A qubit can be 0, 1, or both at the same time, in a state called superposition. This isn't philosophy or poetry. It's quantum mechanics. And when you chain qubits together, something extraordinary happens. If you have 100 classical bits, they can represent one number at a time. Maybe 42, maybe 73. Just one value. But 100 qubits in superposition can represent 2 to the power of 100 different numbers simultaneously. That's over a septillion possible states, all processed in parallel in a single operation. This isn't just faster. It's a different class of computation. Qubits also exploit entanglement, a phenomenon where particles become correlated such that measuring one instantly affects others, no matter the distance. Quantum computers use entanglement to coordinate computation across all qubits simultaneously. The result? Exponential parallelism. Where classical computers must check possibilities one at a time, quantum computers can explore vast solution spaces in parallel. Now, quantum computers come in different flavors. So how exactly does quantum computing tackle climate problems that classical computers can't? There are four main quantum algorithms that matter for climate, and we will only use one as example: variational quantum eigensolvers, VQE. VQE solves a specific problem, finding the ground state energy of molecules. In English, that means figuring out the most stable configuration of atoms and electrons in a molecule. Why does this matter for climate? Because catalysts work through quantum mechanics. A hydrogen catalyst speeds up water splitting by manipulating electron orbitals. A carbon capture material works by quantum interactions between CO2 molecules and the sorbent material. With VQE, quantum computers can simulate these interactions directly without approximations. They can explore millions of possible catalyst designs in parallel. In 2025, researchers at Technische Universität Ilmenau used a variational quantum algorithm to model hydroxide ion transport across electrolyzer membranes, something never accurately simulated before. The result: identification of catalysts that could reduce hydrogen production costs by 35% immediately, or 60% when combined with quantum-optimized solar panels. Quantum approximate optimization algorithms, or QAOA, tackle scheduling and routing problems where the solution space explodes exponentially. Imagine a global energy grid with 10 million distributed batteries. A battery can charge or discharge, store or supply. The grid must balance supply and demand in real time across different regions, accounting for wind and solar variability. Classical computers can't search this space. They use heuristics and approximations, accepting suboptimal solutions. Quantum computers can frame this as a QUBO problem, quadratic unconstrained binary optimization, which quantum annealers are natively designed to solve. A 2025 study at Cornell University applied quantum QAOA to building energy management across a campus. Results: 6.8% efficiency gain over classical MPC, model predictive control. 41.2% annual CO2 reduction compared to deterministic control. Real-time response to solar and wind variability. That's one campus. Globally scale this to millions of buildings, industrial facilities, and grid nodes. The cumulative impact: billions of tons of CO2 avoided annually. Algorithm 3. Quantum linear solvers, HHL algorithm, offer exponential speedups for systems of linear equations, crucial for climate dynamics and atmospheric fluid flow. Most physics problems, including climate dynamics, boil down to solving systems of linear equations. The Navier-Stokes equations describing fluid flow, heat diffusion equations, radiation transfer equations. Classical computers solve these using iterative methods that take time proportional to the matrix size. For a climate model with millions of grid cells and variables, this becomes the computational bottleneck. The HHL algorithm, Harrow, Hasidim, Lloyd, 2008, offers an exponential speedup for certain classes of linear systems. Instead of time scaling as O, poly, M, where M is matrix size, HHL achieves O, poly log, M, logarithmic scaling. For a system with 10 million variables, this is a 10,000 plus fold speedup. Algorithm 4, quantum machine learning, or QML, using quantum neural networks, can parameterize subgrid scale processes like clouds and turbulence in climate models, outperforming classical neural networks. Let's quantify the impact. McKinsey and other research institutions have estimated the CO2 reduction potential if quantum computing achieves its timeline. By 2035, quantum-enabled technologies could deliver 7 gigatons of annual CO2 abatement. That's enough to avoid 0.2 degrees Celsius of warming by 2050. In a world heading toward 3 degrees Celsius of warming, 0.2 degrees Celsius is meaningful. Now for the hard truth. All of this potential depends on solving one catastrophic engineering problem: quantum error correction. Current quantum computers are like building a skyscraper on sand. They have incredible potential, but they're fragile. Each operation introduces noise. After 100 gates, computation becomes garbage. To fix this, you must use quantum error correction, a technique where one logical qubit is encoded into 1,000 physical qubits. This creates a paradox. To harness the power of quantum computing, you need massively more qubits. The industry calls this the qubit trap. You need 1,000 qubits just to create one reliable qubit. At that point, is it still exponential advantage? The answer is yes, but it requires crossing a threshold. Once you have 100 to 200 logical qubits, quantum advantage becomes real. Until then, quantum computers are research toys. IBM targets 200 logical qubits by 2029, requiring 20,000 physical qubits, pushing us towards the fault-tolerant quantum computing era between 2030 and 2040. Here's the truth about the paradigm war. There is no war. Instead, we're building hybrid systems where quantum and classical computers work together. Think of quantum as a specialized accelerator, like a GPU in a data center. The GPU doesn't replace the CPU. It handles specific workloads, neural networks, matrix operations, where it excels. Similarly, quantum processors will be embedded in classical HPC systems, handling molecular simulations, VQE, optimization, QoA, quantum annealing, machine learning, QML parameterizations, linear algebra, HHL. Classical systems will manage everything else: data handling, I/O, error correction feedback, circuit compilation. This hybrid model could deliver 60 to 70% of theoretical quantum advantage, enabling the 1.5 degrees Celsius pathway when combined with other technological breakthroughs. If quantum delivers as projected, climate crisis moves from potentially catastrophic to manageable with aggressive action. If quantum stalls, we're back to classical computing alone, which means older, slower climate solutions. Our margin for error shrinks dangerously. The quantum versus classical computing war isn't a battle for dominance. It's a race against time to deploy a fundamentally new tool before the climate window closes. For humanity, the outcome of this race, measured not in papers or benchmarks, but in degrees of warming avoided, will define whether we successfully navigate the greatest challenge we've ever faced. The quantum revolution is coming. The only question is whether it arrives in time. Okay, if you find this video interesting, please like and subscribe. Thanks for watching, and I will see you next time.